90% of the world's digital information was generated in the last 2 years alone, fueling an artificial intelligence boom that demands massive server farms and nearly infinite inputs. But what if the engine of tomorrow did not require an ocean of information to function? Imagine a reality where a neural network, a computing system inspired by the biological brain, could master complex tasks after seeing only a handful of examples. The current paradigm of deep learning dictates a ravenous hunger for massive data sets to train effective models. This deep dependency creates substantial bottlenecks across the global economy. Training a modern large language model, or LLM, an AI system capable of understanding and generating human text, costs millions of dollars and consumes enough electricity to power a small city. Furthermore, relying on big data inherently limits innovation to the tech giants who can afford to harvest, store, and process it. This counterfactual exploration asks us to envision a radical shift toward few-shot learning. In this paradigm, an algorithm does not need 10,000 images of a defective microchip to recognize a manufacturing flaw. Instead, it requires only 3 or 4. By leveraging advanced transfer learning, the ability of a model to apply knowledge gained from one task to a completely different but related problem, systems could extrapolate patterns with astonishing efficiency. The immediate consequence of such a breakthrough would be the rapid democratization of technological development. If artificial intelligence learned effectively from limited data examples, the barrier to entry for startups and mid-sized enterprises would collapse overnight. A small logistics firm could train a highly specialized routing algorithm using only a few weeks of its own proprietary delivery records, rather than relying on generalized off-the-shelf solutions built on global data sets. This shift fundamentally alters the competitive landscape of the digital economy. Data scarcity, once a death knell for niche innovation, becomes a solvable puzzle. Industries previously left behind by the tech revolution due to a lack of digitized historical records suddenly find themselves at the frontier of automation. The core value proposition shifts from who holds the most information to who can engineer the most effective learning architectures. Consider the medical field, where patient privacy and rare conditions naturally restrict information gathering. Diagnosing an ultra-rare autoimmune disease currently relies on a handful of global specialists manually comparing isolated case studies. A small data AI system, capable of meta-learning, where the algorithm essentially learns how to learn, could analyze just 50 global cases and immediately identify the subtle biomarker signatures invisible to the human eye. According to recent industry analysis, eliminating the need for vast training sets would accelerate clinical trials by years. Pharmaceutical companies could deploy highly targeted models to predict protein folding or drug interactions without needing petabytes of historical chemical interactions. The strategic focus for healthcare executives would transition from aggressive data acquisition to the rapid, localized deployment of highly specialized diagnostic tools. Beyond healthcare, highly specialized manufacturing stands to gain immense operational agility. Aerospace components, for instance, are produced in low volumes with incredibly strict tolerances. When a factory only produces 40 specialized turbine blades a month, traditional deep learning limitations prevent automated quality control from ever gathering enough failure examples to function properly. An AI equipped with few-shot capabilities changes that math entirely. By analyzing just 2.5% of a production run or a couple of instances of a microscopic stress fracture, the vision system adapts instantly. Factory managers could implement real-time defect detection on bespoke, low-volume production lines, drastically reducing waste and ensuring absolute precision without waiting months for the algorithm to catch up. This transformation also rewrites the ethical playbook for machine learning. Today's reliance on massive, unfiltered internet scraping often embeds societal biases directly into the core algorithms, creating discriminatory hiring tools and flawed predictive policing models. When developers can curate small, high-quality, perfectly balanced data sets to achieve the exact same results, the excuse for biased outputs evaporates entirely. Furthermore, the privacy concerns that currently paralyze regulatory bodies would significantly diminish. If a financial institution can train a robust fraud detection model without pooling the transaction histories of 50 million customers, the risk of catastrophic data breaches drops exponentially. Companies could operate entirely within localized, secure environments, utilizing prompt engineering, the practice of carefully crafting input instructions to guide an AI's output, to refine models safely on the edge of the network. This localized approach fuels the rise of edge computing, moving power away from centralized hubs. Instead of sending sensitive information back to a massive cloud server, the processing happens directly on the user's device. A smartphone could learn its owner's unique speech patterns and predictive text preferences using only the data generated within a single afternoon, keeping personal information strictly confined to the hardware in your pocket. The environmental footprint of artificial intelligence would simultaneously undergo a radical reduction. Currently, the carbon emissions tied to training a single massive foundation model can rival the lifetime output of 15.5 standard American cars. Transitioning to resource-efficient architectures means server farms shrink, cooling requirements plummet, and the technology becomes genuinely sustainable on a global scale. This newfound sustainability unlocks applications in remote and resource-constrained environments. In precision agriculture, deploying sophisticated crop monitoring usually requires constant cloud connectivity and massive historical weather databases. A small data paradigm allows a solar-powered drone to learn the specific blight patterns of an isolated 10-acre vineyard using just a few localized images captured that very morning. Farmers in developing nations, previously excluded from the agricultural tech boom due to poor infrastructure and a lack of digitized agronomic history, gain access to world-class predictive insights. The technology adapts to the microclimate rather than forcing the microclimate to fit a generalized global model. This hyper-localization creates a more resilient and responsive global food supply chain. Experts suggest this level of adaptability is the true hallmark of intelligence. Human beings do not require 10,000 experiences of touching a hot stove to learn the danger. One instance is profoundly sufficient. By mimicking this biological efficiency, artificial intelligence transitions from a brute force statistical engine into a genuinely adaptive, reasoning partner. Consequently, the talent required to build and manage these systems evolves dramatically. The industry currently prizes data engineers capable of building massive pipelines to scrape and clean petabytes of information. In a few-shot reality, the premium shifts to domain experts, doctors, engineers, and artists who can curate the perfect 5 examples needed to teach the machine a completely new concept. Look at the creative and entertainment sectors as a prime example of this shift. Generative AI, technology that creates new content, from text to images, based on learned patterns, currently faces massive copyright backlash for scraping billions of protected works. If a studio could train a bespoke animation model on just 20 sketches provided willingly by a contracted artist, the intellectual property nightmare resolves into a transparent, ethical workflow. The artist retains control, licensing their specific small-batch dataset to the studio for a single project. The model learns the exact stylistic nuances required without ever touching the open internet. This protects creators, while still granting production companies the massive efficiency gains of automated rendering and in-between frame generation. As we look toward the deployment of autonomous systems, the stakes of learning efficiency become literal matters of life and death. Self-driving cars currently struggle with edge cases, bizarre, highly unlikely scenarios on the road that do not appear often in their massive training logs. An unpredictable pedestrian action or a uniquely shaped piece of debris can paralyze a system trained strictly on volume. An adaptive model capable of rapid transfer learning processes that novel anomaly instantly. It draws on its fundamental understanding of physics and object permanence, extrapolating a safe response from a single exposure to the new hazard. The vehicle does not need to crash 1,000 times in simulation to understand a new type of intersection. It figures it out on the fly. This real-time adaptability becomes the critical enabler for deep space exploration. A rover on the surface of Mars, facing a 20-minute communication delay with NASA, cannot wait for a centralized cloud to process an unexpected geological formation. It must act autonomously and learn from its immediate surroundings. Equipped with small data AI, the rover identifies a novel mineral structure, learns its visual properties from the first encounter, and immediately begins scanning the Martian horizon for similar deposits. The mission accelerates exponentially, driven by a machine that learns like an explorer rather than a static database. The reliance on vast datasets has undoubtedly launched the current era of machine intelligence, but it remains a brute force approach with severe structural limitations. Moving beyond this dependency is not merely a technical optimization. It is a fundamental reimagining of who gets to build the future and exactly how that future operates. When artificial intelligence learns effectively from the sparse, the rare, and the unique, it ceases to be a mirror reflecting only the massive aggregates of human history. It becomes a precise, adaptable tool for bespoke innovation, ready to solve the specialized challenges of tomorrow with a fraction of the resources.